Hello everybody, this is going to be a presentation on what is friction. And I know we talked about this before, but it's going to be an in-depth look at how it relates back to Newton's second law. So we're starting off in the best way that we possibly can by looking at an amazing GIF, right? Of this cute little puppy that is attacking this poor little cat, right? And we're going to find out at the end what this even has to do with friction. All right, so friction. It's the force of friction between the surfaces, and it depends on the kinds of material it's in contact with, and the force of which these surfaces are pressed together. So the kinds of material it's in contact with. So I'm sure that you've all run through the grass, right? It was nice to be in contact with the grass, but then, oh no, now you're in contact with ice. It's a whole lot harder to maintain your running speed on ice than it would be on the grass. And this has to do with the kinds of material. So we know that if a material is more rough, then we know that the contact force is a whole lot easier. So there must be a lot of frictional forces at play. But when the material is smooth, then we know that there aren't a lot of frictional forces at play. And again, that has to do with the kinds of material. But that's not the only thing that friction depends on. It's the force with which these surfaces are also pressed together. So you have your weight force that is acting down, and then you also have that support force, or that normal force, acting back up. And that normal force indicates to us the force with which you are pushing something together. So again, it depends on the kinds of material that you're in contact with and the force of which you're pushing them or pressing them together. So if we were to look at this track, I'm sure you've all run on a track before. If we were to look at the material of this track, we would say that it's pretty groovy, right? There's a whole lot of grooves and irregularities within those surfaces. So we would say that the frictional force is very present in there. But then let's look at the other GIF of this cute little cat that's being rubbed on a very smooth surface and then being pushed to the carpet. So we can see that it's a whole lot harder to push this cat on the carpet than it would be on the smoother surface. And that is all due to the frictional forces at play. But again, it has to do with the kinds of material and the amount of force that you're pressing down on the surface. So if we were to push down harder on this cat, again, not enough to hurt it, but just a little bit harder, we would see again that the frictional force would be greater and that it would be harder to push this cat in that forward motion because the opposing force is friction. And again, it all has to do with the kinds of material and the force with which these surfaces are pressed together. So, friction. Friction is a force, and it affects motion. So friction acts on materials that are in contact with each other. And you can do this right now. If you put your hands together and you start to rub them together, then your two hands are in contact with each other. And it always acts in the direction to oppose relative motion. So if you're trying to go up and down, then your frictional forces are going to change depending on your direction of motion because the frictional forces are always trying to act opposite of that motion, trying to slow you down in a sense. So when two solid objects come into contact, let's say like your two hands, the friction is mainly due to the irregularities in the two surfaces, so the irregularities within your hands themselves. Again, so if you were moving to the right, so your motion is to the right, then your frictional force is going to be acting to the left. All right, it's going to try to slow you down in a sense. Again, that's all due to the irregularities within the surfaces and the amount of force that is being pressed together with those surfaces. So now that we know a little bit more about friction, I'm going to ask you a little question. All right, so does a car body against a guardrail or a tire against concrete produce more friction? Go ahead and think about this for a little bit. I'll wait. It is against the concrete, right? So a tire is rubber. Rubber is a lot of irregularities within it. That's why you try to groove the road, try to catch it every time that tire moves. And again, concrete, a lot of irregularities within that surface. So the frictional forces between those two objects is going to be very great. And if you have like a smoother surface like a guardrail, again, there's going to be frictional forces at play, but they're not going to be as great as they would be with a tire against the concrete. And that all has to do with the different materials and the amount of force that is pushing them together. But I will say that the tire and the concrete actually causes the car to flip in some circumstances. So again, it's a little bit of give and take there. Let's talk about fluid friction. Okay, so most of you had the idea that fluids were only liquids. And I would say, that was a pretty good idea, but it was only half of the idea. Because fluids are both liquids and gases. A fluid is considered anything that flows. Okay, so again, it could be like air or it could be like water, right? They both flow. We've all seen water flow, maybe through a river gracefully through the mountains, or maybe the wind in your hair or the wind through the trees, right? Both of those are two examples of fluids around us, and a fluid friction occurs as an object pushes aside the fluid. So if you are falling through the sky, air is going to be rushing up towards you, okay? And that fluid friction is going to occur. And it's actually called air resistance. So air resistance is the friction acting on something moving through the air. So whenever I say, consider the effects of friction, make sure that you are considering this effect, especially if you're falling through the air. Okay, so anything in contact with the air is going to be affected by that air resistance friction. So just like our Wile E. Coyote, right, he's falling through the sky or through the air. So we have air resistance that is opposing his falling motion, so acting upward. And then we have the weight of Wile E. Coyote acting down. Okay, so as he pulls that parachute, it's going to increase his surface area. So this is going to allow air resistance to have a greater effect on his motion. So he's going to slow down even more once he pulls that parachute. So again, we all fall down with the same rate, g. But with air resistance involved, we now can fall down at different rates. And it all depends on our weight, and it all depends on air resistance. All right, this is a very important slide. Okay, so make sure that you get this down in your notes. When friction is present, an object may move with a constant velocity, even when an outside force is applied to it. I know, this seems crazy, right? But let's look at our free body diagram. So we know that the car is on Earth, right? So it must have weight because it's being affected by gravity. So that weight is going to act downwards. And now we have the support from the road, right? So the support from the road is going to act upwards on that car. And the support force or the normal force and the weight of the object are equal in magnitude. So they both hold the same value, but they act in opposite directions. So another thing that we know is the applied force, right? Because if this car is moving down the road, then there's something that has to be applied, and it must be the thrust from the engine. So the applied force to the right because this car is moving to the right, but what do we know now about friction? Well, friction is going to oppose that motion. It's going to try to slow down the motion of this car. Now we have to look at our context clues. Constant velocity. Now, constant velocity means when something is moving in a straight line at a constant speed. So again, straight line, it's not moving or changing its direction. And a constant speed, well, that just means it's not accelerating. Okay, so again, it's moving at this constant speed in a straight line. So it has this applied force, and the frictional forces are also acting on it. But what has to happen in order for this car to maintain a constant velocity is that the applied force has to be equal in magnitude to the frictional force. So the applied force is equal in magnitude, opposite in direction, of our frictional force. And that means that this car is in constant velocity. And if we even relate this back to equilibrium, and we found the sum of the forces would be equal to 0. But this object is still moving at a constant velocity, so they would be in dynamic equilibrium. So the sum of the forces is equal to 0. And we know that forces cause acceleration, right? An unbalanced force is going to cause something to accelerate. So if this vehicle is moving at a constant velocity, then we know that it's not accelerating. So we know that the forces must be balanced and that the sum of the forces is equal to 0, and that the acceleration is 0, and that this car is just cruising down the road in a straight line at a constant speed. All right, let's talk about our frictional forces. Okay, so we're going to be introduced to 2 frictional forces. One of them, static friction. The other one, sliding, in parentheses, kinetic friction. Okay, so forward/kinetic friction. Okay, so starting off with static friction. Static friction is the force that opposes the start of motion. Now, looking at this image, I'm sure we've probably all done this before, trying to test how strong we are. Can we start the motion of this vehicle? Well, we would say that in order to get this car started or moving, we need to be greater, or we need to apply a force that is greater than the static friction force that opposes that motion. So again, it's the friction that is at play before you get something moving. So just like this car, it's originally at rest, so we need to apply a force that is greater than the force acting against us in order to change this motion, because again, it's all about unbalanced forces. It's all about creating that unbalanced force in order to have something accelerate or change its motion. So once the applied force is greater than the static friction, the object will move. Again, once the applied force is greater than the static friction opposing that force, the object will move. So let's talk about the next type of friction, sliding friction or kinetic friction. So once something starts moving, the friction actually decreases. So the friction between surfaces that are in motion relative to one another is called sliding friction or kinetic friction. And this is important when you think about your car stopping faster if it's not skidding, right? If your car isn't continuing in that motion and skidding across, your car is going to stop faster. So it's all about acting against that frictional force in order for this car to stop. So again, static or sliding friction. Okay, static and sliding friction. Static friction is that friction that opposes the start of motion, and sliding or kinetic friction is the friction that continues with the motion of the vehicle or the object. So we have a sliding friction equation. So it goes a little something like this. The force of sliding friction between 2 surfaces depends on the normal force pressing the surfaces together and the types of surfaces that are in contact with each other. So the force of sliding friction, or F sub F, equals the coefficient of sliding friction, which is that weird looking M. It's a mu, okay, it's a mu symbol, and the normal force. So again, to represent the normal force, we just put F sub N. Again, the normal force is also our support force, or the support from the ground on the object, if we were to use object on object notation. So again, the force of sliding is equal to the coefficient of sliding friction times normal force. So F sub F equals mu times F sub N. And let's get back to what we were just talking about with friction. And let's draw some free body diagrams. Okay, so the direction of force of friction always opposes the direction of motion. So Dave pushes the sled across the carpet at a constant velocity. So this is my good friend Dave, right? He's pushing this sled across the carpet. And I want you to create a free body diagram for the sled. All right, so not for Dave. I want you to show me a free body diagram for the sled. Go ahead and try your best on it now. Okay, so let's talk about this one. So the key words here were constant velocity.